test match needs just 2 teams and a pitch. Every drop of water which falls on the wicket, whether from the sky or from a carefully controlled sprinkler, affects the way the wicket behaves, and concern over this strip at Trent Bridge can become a national pastime near test matches. To prepare the perfect wicket, Ron Alsop, the groundsman, controls not only how much water reaches the strip, but he also takes great care to drain it, for the soil acts as a store, soaking up rainfall until all the pores are full. The millions waiting for the game take it for granted that Ron's experience will enable him to keep the pitch well drained and, should he need it, there'll always be water available for the grass in dry spells. This programme is about how the water is supplied to Nottingham and what's done to it after use, so that it can be used again. We tend to take for granted our continual supply of water, and in the Nottingham area, the Severn Trent Water Authority supplies water to about 250,000 people. Not just the few litres a day they need to survive, but some 270 litres a day for every inhabitant.
This massive demand has to be met from a variety of sources. The River Trent hasn't been used for water supply since the mid-19th century because of pollution. But Nottingham is luckier than most cities. Just as the roller showed that water can be stored temporarily in the soil, this city is built on a vast store of water, a sandstone aquifer, and no roller could squeeze this store dry. There's a good place to see this aquifer not far from here.
This cellar was dug into the rock about 20 metres below the bar, and most of Nottingham's built on this 220 million year old Triassic sandstone. It's known as the Bunter sandstone. It typically shows large cross-bedding, showing it was formed as a dune in a desert environment. It's very poorly cemented, and the grains are typically quite well rounded. They vary in size from these medium sands to the occasional pebble, but between all the grains are spaces, pore spaces. In fact, 20% of this rock is holes, and it's these holes which give the rock its high porosity. These holes could equally well be filled with water or even oil.
Most of the pore spaces are interconnected, so when under pressure, liquid can move or permeate through the rock. And it's this permeability which makes the Bunter sandstone an important aquifer over much of the Midlands. Not all sandstones are good aquifers, because many have their pore spaces filled with cement, which binds the grains together so that they have lower porosity and permeability. Fine-grained sedimentary rocks, such as silts and mudstones, may contain many spaces between the grains in which water can be held within the rock, but these spaces are so small and poorly interconnected that water cannot move through the rock. They have reasonable porosity, but very low permeability.
Permeability can be affected by other means. The rock here is cut by fractures and fissures of various sizes. Some, like these, related to original sedimentary structures, and some related to the regional stress pattern. These fissures provide additional routes for water to pass through, and so increase the permeability.
The sandstones in the pub cellar were 20 metres below the surface, and they continue downward for another 70 metres. They're exposed at the surface for 150 kilometres northward from Nottingham, up to Teesside. At Nottingham, they dip gently eastwards below younger rocks. Surface water entering the sandstone at the outcrops will percolate downwards until it reaches the water table. below which the pore spaces are full. During this percolation, any impurities in the water tend to be removed by absorption onto the surface of the grains. Where the water table reaches the surface, water will flow from the rock in the form of springs. And where the water table is just below the surface, shallow excavations can be made to reach it.
This large system of cave-like cellars, just a short walk from the pub, was dug into the side of a cliff from the 13th century onwards, and the inhabitants had only to dig a short distance down to reach water. As water was taken out of these wells, fresh supplies came in round the walls of the well, often, unfortunately, more slowly than the rate of demand. As the population increased, the demand increased, so local engineers had to dig deeper wells to tap more of the water table.
During the 19th century, wells were dug deeper to extract water from greater sections of the aquifer. This one is capable of producing far greater quantities than the shallow medieval wells. But how do you extract water from this depth? Still in working order, this vast beam engine on top of the well pumped water for Nottingham for over a century, maintained by a small army of stokers and engineers. In the 1960s, this relic of the Victorians had to yield to the demands of efficiency. No one need tend these replacements, which now extract water from the well and pump it to a storage reservoir for distribution. Methods change, but the net effect is constant. Water is removed from the well, and what effect does that have on the aquifer? Any rainwater falling around Nottingham which infiltrates through the topsoil will eventually reach the Bunter sandstone aquifer and replace the water being extracted by pumping. The water table within the aquifer can be kept fairly constant on a long-term basis only if water is extracted at the rate at which it's being replenished. As a single borehole is pumped, the water table is drawn down around the borehole into a cone of depression. The size of the cone depends on the pumping rate, the depth of the borehole, and the permeability. Coal mining will locally affect the bulk permeability of the aquifer by fracturing the rock above the mine workings. To extract the optimum amount of water, the boreholes must be spaced fairly regularly throughout the aquifer. If boreholes are too close together, their cones of depression overlap. The water table is lowered in the vicinity, resulting in an effective shortening of the borehole, and so less water is available. The first pumped boreholes in Nottingham were near to the city and were fairly closely spaced. This pumping resulted in a rapid lowering of the water table. Later, boreholes were drilled further from the city to tap other parts of the aquifer. And now a steady state is maintained by limiting the abstraction to keep the water table constant. Treatment for this water consists only of chlorination before it is pumped to a storage reservoir and later distributed. supplying about 65% of the area's demand. But where does the rest come from?
Well, these massive valves at the bottom of the Derwent Dam control the flow of about 250,000 cubic metres of water a day, which goes down to the Midland cities, including Nottingham. The water, in fact, is piped away through these massive pipes down a gravity-feed aqueduct about 70 kilometres to the south, where it meets distribution centres which supply water locally into Nottingham and Derby. But why build a dam here, so far away from these major cities? The moorlands of South Yorkshire and Derbyshire have a high average rainfall and are founded on 350 million years old carboniferous rocks known as the Millstone Grit series. This comprises thick, gently dipping bands of hard, well-cemented grit with interbedded shales, altogether an impermeable sequence of rocks that inhibits infiltration and promotes surface runoff. Low bedrock permeability coupled with high rainfall makes the area attractive for water resource development involving dammed valleys and reservoirs. And work started in 1903 to build 2 masonry dams at narrow points in the Derwent Valley, one here at Derwent and the other at Howden, a few kilometres upstream. Deep excavations into both the valley floor and sides were filled with concrete, providing a cut-off curtain that ensured a watertight seal around the sides and bottom of the dam. The weight of the dam itself is all that's needed to balance the downstream force of the impounded water. Construction took 12 years, and water was finally piped to Nottingham in 1917. Well, the rocks around here provided most of the raw materials necessary for dam construction. And you can imagine they've got to be pretty strong to withstand all this buffeting, especially when the dam overflows, as it does most winters. These blocks here are fairly typical Millstone Grit series. It's actually a coarse-grained, gritty sandstone. Now, you can't see that very well from here, so let's go and have a look at a cleaner example. Oh yes, here's a nice gritty band, and you can see that the quartz grains are subangular and they range up to about 1 centimetre in size. Now this rock is very well cemented, the grains are held firmly together, and that means it's non-porous. Contrasts in that respect with the Bunter sandstone aquifer that you saw earlier, which is very friable and very porous. Now another thing about these Millstone Grit blocks is that in the natural state, as in a local quarry, they're very well jointed, and that means that they can be easily fashioned into massive building blocks like this, ideal for dam construction. But the natural rocks around here aren't all just gritstones. This fine-grained shaly material at the foot of the dam, it's a fairly impervious, compact form of mudstone, forms relatively thin bands between the massive gritstone units. Now, during dam construction, the trenches you saw earlier being excavated were designed to intersect several of these shale horizons. And the reason for this is that once the trench was filled with concrete, then the intersections between the concrete and the shale bands provided a network of underground watertight seals all around the dam, partly forming also a cut-off curtain underneath it and an apron behind it. And they've stayed that way ever since. Now, the beds here look pretty horizontal, but imagine what might happen if these beds were dipping. What happens is that water will percolate down through and between the joint planes in the gritstone units, and it will begin to pond up where the grit shale intersections are. Now, this lubricates the shale horizon and reduces friction there. So if the sequence was dipping, the massive blocks of gritstone could start to slide under gravity. And on a large scale, these form landslips that are particularly common all around the Peak District, forming hummocky ground with concave slopes in the hillside behind where the material's been removed. So it's very important before dam construction to carry out a thorough site investigation to examine the geological conditions and make sure that they're appropriate for dam construction. Now, the Derwent Dam was finished in 1912, but nowadays masonry dams of this kind would be too expensive to build, and instead reinforced concrete dams are used in rather narrow valleys, whereas in more open locations earth-filled gravity dams would be used. This is the Lady Bower Dam, about 5 kilometres further downstream, which was completed in 1945. The geological foundations are rather similar to those of Derwent Dam, and again this means that there's a deep concrete cut-off curtain underneath the dam. The dam has a clay core, flanked by a large mass of shaly earth, built out on a gentle slope downstream. I'm standing on one of the masonry towers, and below me there are a series of inlets where the water's drawn off. But when the reservoir is very full, then water goes down the overflow to emerge at the bottom of the dam. And this is where water from both the overflow and from sluices within the dam emerges into the River Derwent. Now, Lady Bower Dam was built to increase the overall storage capacity of the Derwent reservoir system. This extra storage capacity was needed to ensure that an adequate supply of compensation water was available after abstraction to maintain the southerly flow of the River Derwent during the summer months. A river is a living environment, and a minimum guaranteed flow rate is needed to maintain oxygen levels, keep the river clean and the water pure enough for abstraction further downstream. So Lady Bower Reservoir is allowed to fill up during the winter months and to empty slowly during the summer months, maintaining this minimum flow rate. Not only that, but the regulated river is a natural aqueduct, and so once more tributaries have joined it downstream, more water can be abstracted.
And some 60 kilometres south of the dams, the Severn Trent Water Authority pump and treat 27,000 cubic metres a day here at Church Wilne. Screens at the intake remove coarse silt and debris before the water is pumped into a large storage reservoir. Aeration improves the quality by removing odours and dissolved gases, and also by helping precipitate out some dissolved salts. From storage, the water passes into the works through mixers where coagulating agents are added, then on to reaction tanks. Here, the water is passed upwards, slowing as the cross-section of the tank increases. Previously suspended matter stops moving upwards as the velocity decreases and is removed by suction at a particular level through a canvas cone suspended in the tank. Settled water passes to the top of the tank and away. This process removes nearly all suspended matter, and sand filters and carbon pressure filters like these remove the last fraction. Chlorination is all that's needed before the water is piped into the city for consumption. How can the supplies of water to Nottingham be increased in the future? We've already said that groundwater pumping has reached a working limit, and so is the supply from the Derwent Valley reservoirs. The cost of treating water from the Trent is considered prohibitive, and the flow of the less polluted Derwent is too low in hot, dry summers when demand is highest for more water to be abstracted from it. So the Water Authority has planned a new reservoir at Carsington to be used for regulation of the Derwent. It will store water pumped up some 150 metres from the Derwent in winter, when there's plenty to spare, and in summertime release it back to the river to supplement the flow. This water can then be extracted at the Church Wilne treatment works.
So the supplies for the area are safeguarded for some years to come. But the work of the Water Authority doesn't stop with supply. At the beginning of the programme, we said that the River Trent has been too polluted to be used for supply since the Industrial Revolution. We've learnt a lot about pollution since that time, and the river's much cleaner now. But we still do a lot of unpleasant things to that water from the tap. Apart from the obvious organic wastes, we add detergents and bleaches in the home, and industry pours toxic metals and chemical waste, as well as organic waste, down the drain. Those wastes don't just flow straight to the river. Instead, they all flow in Nottingham to Stoke-Bardolph sewage works, where they're treated before returned to the Trent.
About 150,000 cubic metres a day flow in from Nottingham. The first stage in treatment is to remove grit and other dense materials in these settling channels. The grit is buried along with rags, wood and other floating debris picked from the crude sewage by these mechanical rakes. Sedimentation in large tanks removes about 30% of the organic matter. This is pumped away to the sludge digestion plant. Here, in a warm, oxygen-free environment, bacterial action breaks down the organic matter, producing methane and carbon dioxide, and some 200 tonnes a day of relatively inoffensive sludge, which is pumped away onto farmland for use as a nutrient, whilst the methane is used for power generation. The settled sewage passes on to an aeration plant. Here, it's mixed with a bacterial culture and aerated with these rotating paddles. The organic matter in the sewage is broken down by the bacteria into simpler and relatively harmless constituents. This process consumes oxygen, which is made available by aeration. To separate the sludge from the effluent, settling tanks are used, where the sludge falls to the bottom and is returned to the aerators. The resulting effluent passes on and back to the river.
Many things have happened to this water since it fell as rain like this, but soon it will reach the North Sea and continue through the hydrological cycle. And we can go on borrowing water from this cycle forever, as long as we understand the cycle and we care for the water in it.